Hello, I'm Karel Beneš, and together with Lukáš Burget, we were looking into how can we introduce some augmentation into the training data of language models so that they can cope with difficulties from the acoustic condition. When you just train your language model, you just make it optimize probability of some text that you have collected from somewhere from the internet, or maybe it's coming with your challenge data. In practice, it means you give a sequence of words to your language model, and now you ask it to predict the following word. However, in practice, if you use the language model to rescore some actual ASR outputs, there may be errors. And you would still like the language model to give you a reasonable prediction of what follows, and you would like the language model to give you something more smart than just saying, oh, this is linguistically impossible, I will give you my beautiful unigram belief of the world. So what we do is we introduce ASR-like errors in the training so that the language model can actually learn how to live with them. If we want to introduce a substitution, it's actually extremely simple. We just substitute the word. I will try to use this device. Like if we wanted to replace this good, we will just replace it with some other token. This is also done when you train your standard BERT model for whatever NLP task. It gets more delicate when you go for deletions or insertions. If we would like to delete this good, we need to somehow, we can't just get rid of it because the computational graph of the neural network, whatever that is inside, calls for some input in there. And we cannot put a mask there because there will be no masks in the output of ASR. So what we do instead is that we get rid of the time step entirely. And when the language model is at this position, we actually pretend that the good, which we have just erased from the input, has happened. So we feed it with the following token and still have the language model just predict what goes next, so this end of sentence mark. Conversely, if we want to emulate insertion, we do the opposite. If we want some extra in front of this good, we simply put it in there in the input. And now the question is what to do with the target, because we are suddenly making that out of blue. And we follow the same logic that we pretend that this error has not really happened. So even though we have this extra token in there, we keep the target token which was in the previous time step because we still want the language model to predict what is the real following word. So that's the technical part. Now comes the interesting questions. Where do we actually get these errors? And we ended up only comparing two models. One of them is a 0-gram error model, which we were working with during the Chime 6 challenge, where we only tune the overall rates of substitution, deletion, and insertions, but we don't care about modeling what words get replaced by what, and we just take a sample from a uniform distribution over your full vocabulary. This brought us some nice improvements, so we were like, yay, now it's time to do something smart. And the logical next step was to go for a unigram language, a unigram error model. So what we did was we transcribed the training data, we took 100 best transcriptions of that, aligned it to the reference, and collected statistics. How many times does this word get replaced by this one, or how often does it get deleted, what words do get inserted. With this error model, there is nothing more to tune because you have the statistics and they tell you what to do to your data. So these are the conceptual error models. In practice, we ended up comparing 7 systems. One of them is baseline, which is only trained on the actual clean data. Then there is the 0-gram model, where we blindly introduce errors. Then there is this unigram error model, where we have collected the statistics from training data. And we also have an Oracle version thereof, where we collected the statistics from the development data. So this can serve as the top line to show us how much can we get if we know the actual errors that the ASR makes. For reasons that will come up later in the results discussion, we also compare this to a target augmentation, where we simply change the target label. And we not only change the target label, but we also combine this with introducing the deletions and insertions, just as I have shown you on the previous slides. And also we compare this with label smoothing, which can be thought of marginalizing out this noise and really like taking the expectation over replacing the target with any target from your vocabulary. We evaluate on Chime 6, where our ASR provided by Martin Kocour, thank you very much, was based on a CALDI. So the acoustic model is a stack of CNN and TDNF layers. We used a trigram model for the first pass decoding, and the overall border rate is quite high. It's around 48%. It's a single system, and we didn't win this challenge. The language model that we use for our work is an LSTM of 2 layers, 650 units. And we apply it to NBEST rescoring. We took 3000 NBEST to hopefully avoid search errors. But I rerun the same with 100 best, and the story remains the same, just the numbers are slightly worse. We carry over hidden state so that we can exploit the fact that we are actually dealing with 2-hour sessions, not just 10-second segments. And an important thing is that when we were training language models with different augmentation schemes, we actually trained a couple of them with different dropout setting. And this is a point where we actually got what we expected, because when we were searching for the optimal overall regularization rate, because the augmentation, regardless of our motivation, does introduce some regularization, we actually got the baseline to really enjoy a strong dropout of 0.7, whereas whenever we introduced some augmentation, this optimal dropout rate dropped to somewhere between 0.3 and 0.6, and it was not really sensitive to the exact value in between. So getting to the results, here are the word arrays on the development portion of QIIME 6, presented as an interpolation between the Engram model, which is in the left, the one that was used for the first pass decoding, and the LSTM scores only in the right. Now, the black curve at the top is the baseline, which is nothing to frown upon because it still improves quite nicely over the Engrams only. But the interesting thing is that the best guide, the blue model at the bottom, is actually the input 0-gram errors, where we didn't really model anything of the actual ASR errors. And this unigram error model, of which we really had high hopes for, those are the 2 hopeless green curves at the top, sitting there next to the baseline. So we were really trying to understand, why is it like this? Why do the unigrams not really provide any additional improvement? So we checked for the overall amount of augmentation that's done. So we reduced the amount of the 0-gram errors to the level of the one that's driven by the statistics, and it decreased, but by a tiny bit, it still remained the best one. We got rid of outliers, like errors that were only observed once when we were collecting the statistics, so that they don't screw it somehow. Nothing really changed. So we said, okay, maybe this is just regularization. And that's why we went to kick the language model hard by changing the labels, which gave us the red curve. I can't operate this thing, sorry. Which gave us the red curve that's actually doing the target corruption. And you can see that even though it's not as good as doing all of the augmentation at the input, it's still providing some nice improvements. And interestingly, if we did label smoothing, it does not give so much of an improvement, which also suggests that this is all about kicking the language model very hard, because label smoothing still tells the language model, this is the correct token, just keep some probability for the other guys too. Whereas with the red models, we really told them, no, it's this word that you should be predicting, and it was still better than the label smoothing. We also tried what happens when we interpolate between the target augmentation and input augmentation, because they seem orthogonal, so maybe we could get better even than the blue curve. Turns out, no. Even if we not only did interpolation, but we had some like extras around, it was still moving just in between the red and the blue curve, never really getting better than the input 0-grams. So this was on the validation set, which is still a little bit of cheating because we were tuning some hyperparameters here. So moving on to the test data, which is the right column here, you can see that the overall story basically holds. The baseline improves over just using engrams, and the input 0-gram augmentation gives you the best improvement over that. The target augmentation provides less of an improvement. In case of label smoothing, it went away altogether. And interestingly, the input unigram oracle corruption actually seems to be missing something. Probably as the statistics were estimated on the small validation data, as they were quite sharp, the model has actually learned something about errors, which doesn't really apply to this new set, whereas the actual unigram error model, which was trained on the train data, had those statistics smoother, so moving to a different evaluation set doesn't hurt it. So much for order rates. We also looked into a different aspect of this input augmentation, which is how does perplexity behave when we introduce these changes in the input. We didn't do this with the targets because it doesn't really make sense to measure perplexity with corrupted targets. So what I'm showing here is a histogram of perplexities under different realizations of that noise in the input. And the blue curves represent two models. The red one is a baseline, which has not seen any of the corruption during the training, whereas the blue is a model that was exposed to these augmentation or the corruption in the input. I have centered the perplexity so that we can compare it, because otherwise they were sitting at different absolute values. It was like 220 for the baseline and 180 for the model that was exposed to this augmentation. And actually, the message here is good. This perplexity is reasonably stable. If you have your language model produce perplexity in the range of 180, then the change that we are getting here, like plus minus 2, is not something that should make you really like select this model over that model and expect to get better order rate. So it's well behaved, it's smooth, we would like it. So maybe this could even predict the order rate better. But here we have a negative result because it doesn't really tell you anything more than the regular perplexity. And like there is no significant, nothing significant that we could get from here. So to sum up, we propose a very simple augmentation scheme that's basically free computation-wise, because the thread that's preparing data for your training can introduce those little edits very easily and the GPU will not notice. We got very nice improvements on Chime, nearly doubling the gain from neural language model rescoring. We also applied the technique quite blindly to another data set from the OpenSat challenge, and we again had some improvement, although it was not so big because the overall error rate was lower, so also the room for improvement was not so big. The perplexity measure that's kind of defined by this augmentation scheme is nice and stable. However, it's not a better predictor of the final error rate. So for early stopping or model selection, go with your well-tested perplexity computation code that you are using for years. In stark contrast to our original motivation, this is not really adapting the language model to ASR errors. It seems to really be a regularization scheme that helps the language model to somehow learn better, but not to fit the ASR errors as we had hoped for. As for future directions, there are two sub-branches that we would like to look into. One is moving these two subwords, where we know that not all subwords are created equal. There is big difference between the initial one in a word and those following. So maybe we should put some focus here or there, but we don't know. We didn't try that. And the other thing is we would really like to see the smart augmentation do something useful. So we are thinking of how to actually make the statistics-driven augmentation stronger, because what we saw so far is that it's more about just kicking the language model rather than providing information. So we would like to combine these two into something that's also following the motivation. Our code is public on GitHub, so we will be happy if you use it or file an issue, unless it's for me to document it properly. Thank you for your attention.
Thank you very much. Comment? Questions? Yes.
Thank you. This is a really interesting approach and really simple and works. Have you, I might have missed this part, but have you also tried to augment your training data for the language model just with the recognized output of the training data?
Not directly. So we would not do this on the whole segment level, but we were for the unigram model, which has failed horribly. We collected the statistics really on the unigram level. So we just learned that this word is usually replaced or misrecognized for this word, or it's this likely to get deleted.
So you could bias because you have the correct test. You could build a language model that would technically should perfectly recognize your training set, right? So all the errors in there, these are all hard errors, and they might be actually useful to learn or simulate what kind of errors you have to deal with in your model.
We hope that would be the case, but it wasn't. And it was not even the case when we took the Oracle statistics, even on the development set where they were really matching.
Questions? Yes. Okay, I have one question. You speak about data augmentation. So how much data do you generate?
We do this on the fly. Okay. So every time we get some chunk and pass it to the LSTM to learn on it, we apply the augmentation scheme. Okay. And overall, we went until full convergence because this data is not too large, so we could afford that. It was like 30 epochs or so. And as we introduced this augmentation, we didn't really see what, for instance, ASR people observed that with augmentation it takes longer to converge. Here it was like in not more than 10% extra needed for convergence.
Okay.
So it's nearly infinite, as much as you would like.
Okay.
Can I ask a question? You're working in an area where the error rate is quite high, 46, 48%.
Yes.
And then you get down in a good situation to 46, from 48 to 46, something
yes.
like this. So what about the error area of, let's say, 10%? What do you think your method is going to work there as well?
It does.
The relative improvement, are you going to see that as well? What do you think?
We actually have had one experiment in 10% order rate scenario. We were actually rescoring something that already had Kaldi RNN-LM scores in there, and on top of that I applied this custom language model. And without this augmentation, the absolute improvement was like 0.3 or 0.4, and with the data augmentation, it went to astonishing 0.5.
Okay, thank you.
Okay. More comment? No. No questions. You have presented 7 augmentation schemes.
That's
okay.
Correct. One of them is baseline.
Yes. Have you tried to mix these patterns with schemes?
We actually tried mixing those two that perform the best, the input 0-gram corruption with the target corruption, but it didn't provide any further improvement. It was really just like interpolating between the two, like in terms of the final error rate. So we tried, but this didn't give anything useful.
Okay. Did you try to analyze the errors?
No.
No. Okay. Because you obtained small improvement, but in which cases this brings something for which kind of errors?
I don't know. I was happy with just the number. I didn't analyze like what's the occurrences that get improved.
Thank you very much.